Okay, so we're taking that section, chapter 13. Okay, so we introduce a function of two variables, okay, and we talk about the domain of this function, how we're going to operate. It's a function that the domains are coming from the R2, okay, collection of points in two-dimensional space. So we call it a function of two variables, and it can come, from any dimension, but we're focusing on the 2 and the 3. But the range of these functions are going to be subsets of real numbers. So in the range, we have real numbers. So, we can use any theorems from the past. But in the domain, you got to be careful because in the domain, you are going to be in a two-dimensional or three-dimensional. So what we did, we just focused on the notion of the function, the definition, and the domain, and eventually we talk about the limit of the function. Okay, so we just extend the notion of the limits from a function of one variables to the function of three variables, okay? And that was the actual definition that we extend from a function of one variable. So as usual, because the range of these functions are numbers, so we're just comparing these numbers together, so that may make sense to talk about the ideas like, when x and the y getting closer and closer to the x0, y0, then the difference of these two numbers, if you like, or the numbers are getting closer and closer to the zero. Okay, so eventually we arrive at the similar things in calculus 1. But we got to be careful when you're dealing with the difference between the points in the domain. You are in two-dimensional, so you have to use the norm. But if you're comparing the value of the function and its limit, you are in the case system of the real numbers. So the difference is a number, okay? So we discussed this one. So as soon as we did the definition all right, we were able to use the various theorems from calculus 1. So basically, if you have a polynomial function, in this case, polynomials of the two variables, so all the limits are going to be kind of direct substitution. Okay, so these are the ones we did. So read it carefully to be prepared. And we end up with the two important examples. Examples like 0, 0, okay, in determinant form that we're going to get in these parts. It's natural to get the indeterminate form because you're dealing with the numbers. But you got to be careful, we cannot use the L'Hopital rule. So it's going to be limited to the case that there is going to be a common factor, of course. So find the common factors by factoring, or if you need, remind yourself that in the radical expressions, you may have to use the rationalizing, the radical expressions on the top or on the bottom to get it. So these are the examples that we did. Any question? So far, so good. But there are a group of problems. Mostly you want to find the limit of this function at zeros, and the method is going to be different, okay? So you got to be careful. They are going to be a little bit more involved, and in fact, good problems. So we get a number of these type of cases for for this week, if you like, or these in this chapter. So that's the example number 6 that we're going to consider. We continue, and this is very special one again. Okay, so we are going to be dealing with the limit of the function again, but we continue with these examples. Okay, so this is kind of leftover from that section that we start. We are still, so let's say we are in. Okay, let me just give the date for this one. So today is, what is it, Tuesday? I want to post this one, just make sure you get this time all right. Okay, so we are going to continue with that section. So we are in 13.2 again. So we are dealing with, there are a couple of things about the limit of a function. Okay, so this is going to be the limit of of functions, if you like. functions of several variables again, or two variables in this case. So there are a couple of things that we have to know. So let's start with this example, forget about the 6. So the first group is this one. This is different from whatever we did before. So find the limit. Find the limit. Let's see what is special. You have this one all over the places from now on. So the limit is mostly at 0, and you want to find the limit of 5x squared y divided by x squared plus y squared, but it's going to be at 0. X comma y goes to 0, 0. Okay, you want to find this limit. Let's see what is special about this one. Okay, the top is a polynomial, of course, polynomial x and the y, and the bottom is a polynomial. So as we did with the others, we substitute. Okay, we do the direct substitution. But if you do the direct substitution, that gives you 0, 0. Okay, so the solution is going to be, so as usual, I just substitute. So I just repeat it. So if you directly substitute, this is going to be x comma y goes to the 0, 0. If you direct substitute, that gives you 0, 0. Okay, that was the case. Again, we talk about it. You are not going to use any L'Hopital rule in this case. For the previous problem, we tried to find the common factor eliminator to be able to do it. In this case, you are not going to have such a common factor. You are not going to have such a common factor. So you are going to take another approach, if you like, method in order to take care of these functions. Look at the structure that they are very special. Okay, you cannot find many of these. If you think about this function like a kind of a product of two functions. Okay, if you consider as a product of two functions, you see, note that this is a kind of a method that sometimes we use in calculus 1. Then we can extend it to this, to this level as well. Okay, so what we are going to do is, if you consider it this function, look at this one, 5x squared y. Sometimes we use this one in calculus 1 and mostly in calculus 2, this type of ideas. You see, if you break it in two parts, so the parts that I'm going to break, I give the 5y here, okay, 5r or 5y divided by 1, and the leftover is going to be what? It's going to be x squared over x squared plus y squared. Okay, so I change it into a kind of what? Kind of product of two function. Okay, the product of two function. So, we're just going on informally. So informally, if you like, now your limit is going to be, okay, the limit would be 5x squared y over x squared plus y squared. Okay, this is x comma y, which goes to 0, 0. So it's going to kind of a limit of the first one, limit of the 5y, when x comma y goes to 0, 0, okay, times the second function, if you like. So, it's going to be the limit of the second one, which is going to be x squared over x squared plus y squared. Okay, then you want to find the x and y goes to 0, 0. That's going to be the case. So the limit of the first one is the 5y when x and the y goes to 0, 0 means y goes to 0. So in this case, this would be 0. So you have to find out something about this one. Okay, so how are we going to handle this second one to be able to do it? Okay, so if you want to compare it with the calculus 1 or the operation that you did in calculus, you see, I just put it over here just to recall what you did for this type of ideas in calculus 1. You see, remember in calculus 1, if you want to find the limit of the x squared, sine of 1 over x goes to 0. Do you remember this one? What is this limit in calculus 1 or in general? Anybody? Any idea? Or do you remember this? Any suggestion for the solution? It's very, very similar to this example, and that idea is very popular. It's equal to 1. No, you're not right. It's not 1. Any other idea? If you break it into this type that I did, it's going to be limit of the first one. Limit of x squared, x goes to 0 is 0. Some people, they say, oh, I use the product rule. Since the limit of the first one is 0, as is here, they say, oh, the limit of the, okay, all of them is equal to the 0. Yes, 1. Yes, but this method is not correct because the limit of the second one does not exist. You know that the limit of the sine of 1 over x equals to 0 does not exist. But we can use the squeeze theorem. Yes, 1, you're right. One way to do this is the squeeze theorem. The squeeze theorem, remember the squeeze theorem? The sine of 1 over x is going to be between 1 and -1 all the time. You just multiply both sides by x squared. Okay, that gives you x squared sine of 1 over x less than equal to the x squared. So you find the limit of the negative x squared, which is going to be 0 when x goes to 0. And you find the limit of x squared when x goes to 0, that would be 0. So from the right and the left, you squeeze it. So by the squeeze theorem, the limit of the middle one, x squared sine of 1 over x, x goes to 0 would be equal to the 0. You see, this is the way you do it in calculus 1 or in general to do this type of idea. Okay, so you cannot use the product rule because the limit of the second one does not exist. But if you want to do this one in a kind of advanced level that we are now, or even calculus 2, there is a theorem. The theorem is going to be, you see this second function? This second function is always between -1 and 1. The function that satisfies this condition, we call it a bounded function. Bounded means the value of this function is always less than something. So this is a bounded function. And this function, the limit is 0. So quickly you can prove that the limit of the product of two functions, the limit of the product of two functions, for which the limit of the first one is 0, and the second function is bounded function. This limit is always 0. You can use the squeeze theorem all the time. So if it's going to be cosine of 1 over x is between 1 and -1. So since it's between -1 and 1, it's bounded function. So that's 0 and the bounded function, that gives you 0 right away. Okay, this is the idea that we use in calculus 2 quite a lot when you want to find the limit of the sequences. So we are going to use the similar idea here to be able to do it. You see, it's so popular in calculus 3. So this is 0. You can prove that x squared over x squared plus y squared is a bounded function. Bounded function, you see the sign. The sign is a bounded function because the absolute value of a sign is always less than 1. Look at this. X squared over x squared plus y. Note that. Can you see it? X squared over x squared plus y squared is less than what? Any suggestion? It's a fraction. You see x squared is on the top. X squared plus y squared, both of them are positive numbers. So you have a fraction whose denominator is bigger than the top. You know that if the denominator of fraction is bigger than the top one, this is called what? We call it a proper fraction. So this means this is always less than 1. Okay, because to get the x squared is more than the top. The bottom one is x squared plus 1. So this function is a bounded function. This function is a bounded function. If you just think about a similar argument over here, so this is a bounded function and this is 0, so automatically this limit would be equal to the 0. Just using this type of idea of 5x squared y over x squared plus y squared, x comma y goes to 0, 0. This must be equal to the 0 to get this idea. Okay, any question? But you haven't proved it yet. You see, this is calculus 3, so you have to give us all the details of this proof. Okay, I let you do it in short form, but I want to convince you that this limit is equal to 0. It's very important techniques, and it's going to be all over the places when you're dealing with various functions, when we get to the derivative continuity. So you can guess this is going to be equal to the 0. So what I'm going to do for you is I'm going to just give you a kind of proof why this has happened, or how we're going to write it down. Okay, so that was a kind of a motivation, the model to do it. So when you want to solve this, you say, oh, it is 0. Why it is 0? You are going to tell us that. What do you want to do for us? If you want to prove it to be 0, so you have to show that this difference, you see, you claim that the difference of 5x squared y over x squared plus y squared minus 0. So you have to prove that this difference goes to 0. That's a percentage of error. So we say, oh, I'm going to simplify it for you. It's going to be equal to what? 0 would be out. Use that absolute value notation that we're going to have. So it's going to be the absolute value of, and that's it, the absolute value of the top. No, absolute value of the bottom. But the bottom is positive, so it's going to be x squared plus y squared. The top of 5x squared, you don't need any absolute value. But for the y, you do need it. So we are going to break it into this part. So it's going to be something like x squared, absolute value of 5y. Okay. Now look at this part. This part, as we put it over here, is less than or equal to 1. So this means this is going to be less than or equal to the absolute value of 5y. You don't need the absolute value for 5. So it's going to be 5 times the absolute value of 5. So remember, I want to show that this goes to 0. So I just repeat it. So what I have is the 5x squared y over x squared plus y squared minus 0. You can say that this is less than or equal to the 5 absolute value of y. Okay. So at this level, you can answer the question right away. This is the way you say, or you say, oh, okay, this is it. If, like the squeeze theorem that we say, if x comma y goes to 0, 0, so then y goes to 0. When y goes to 0, so this part goes to 0. So this means 5 times the absolute value of y goes to 0. And if this goes to 0, like the squeeze theorem, so the other part goes to 0, and then you're done. Okay, so if you like, I put it over here. So this is it. So that would imply that the 5x squared y over x squared plus y squared goes to 0, and the limit would be 0 right away. Okay, I'm going to rewrite it for you a little bit so that you get the idea. Any question? Make sure you understand this method. That will help you quite a lot in this course, because there are a group of functions of this format, and you should be able to identify. You should have to, the point is just find something like this that guarantee that this is going to be bounded function. Okay, as I said, in future, bounded function, the limit 0 is 0 right away. But since this is just the beginning of a notion of the limits, and that give you a better understanding to get to get this part through. So this is what I did. So I go to the next page to finish it. So basically, what we proved, and this is it, we proved it. So we can say that the limit of 5x squared y over x squared plus y squared when x comma y goes to 0, 0 is going to be equal to the 0, and then you're done. Any question? Now, if you are going to be a math major, I won't let you go. So I'm going to question you. You see, I question you. This is fine. It's the idea. But look at this one. If you need more, somebody may say, oh, I didn't get the feeling that you got this is right. So this is, look at this one. This inequality that I got over here. You see, this inequality did the job for you. But if you want to connect it to the definition of the limits, or if you're going to be a math major, so you have to give us more details. So these are going to be the details if you are going to be a math major. You see, I would be fine with this solution, but if you are going to be math major, they say, oh no, we are not convinced, just prove it for us. I say, okay, we prove it for you. For the math major, or nice to enjoy. You see, if you want to enjoy it, this is it. You're not going to be convinced. You say, oh, what you did so far is you just prove this one for us. The 5x squared y over x squared plus y squared. You want to estimate it. So what you did is just estimate it for this. But you need the norm. Remember when x and y goes to 0, 0, the norm would be radical x squared plus y squared. So this is the way you're going to connect. You say, oh, okay. So what I do for you is this is y. The absolute value of y, I change it to the radical y squared. You see that's going to be radical y squared. Now I know that the y squared is less than x squared plus y squared. You see, look at this. It's going to be 5 times radical x squared plus y squared. But look at this one. Remember the norm of x comma y minus 0, 0. This norm is what? It's the same as the norm of the x comma y, which is going to be what? Radical x squared plus y squared. So if you connect these together, so what you did prove really is you prove that the 5x squared y over x squared plus y squared minus 0 is less than equal to the 5 times a norm of, you see, norm of x comma y minus 0, 0. And nicely done. See, I find a relationship between those estimations that we're going to do. Now you can say that I can say that if x comma y goes to the 0, 0, so this parts go to the 0, 0, then 5x squared y over x squared plus y squared goes to 0. Okay, and I did prove that the limit of 5x squared y over x squared plus y squared when x and the y goes to 0, 0, the result is 0. You see, one more step. This is you go with the epsilon delta definition of a limit of the function. So these type of methods are very, very important. If you want to be serious and prove things, this is going to be end up the solution here for you. This type of inequality, you may have seen it in calculus 1. For any problem of the limit of the function, you can always have this type of inequality. This type of method was done by the Cauchy, so we call this type of equation Cauchy inequality, and then we can do it for all the problems. But in this course, as long as you get this connection, you can make it short. This is nice really to go 2 more steps to give us a nice proof, okay, of the fact that this limit is going to be equal to the 0, 0. So you will see this problem in a couple of other places, okay, to be able to do it. Any question? I just want you to see the trick that use, okay, for this type of function, and that's a very important one. Some people try to avoid this, and they cheat. They change this problem x and the y, they're using the polar coordinates. They change it to the short form. If you do it on the test, I don't accept it, okay, because it's important for us to learn this method. This is a very crucial method for the function of several variables. It doesn't matter whether you are a math major or you are not. So you will get one of them. And from time to time, you see it. So it's one of those things that, you enjoyed it, the fact, and you don't have to memorize it. So we come back to this one again. But for the time being, this is all we have. Any question? So read it carefully, okay, and we are going to see it again. So the case of the 0, 0, so that would finish this case of 0, 0. These two cases are factorable. You do it right away. But this case is quite different. If you get a 0, 0, you will learn in a minute later that there are cases that this limit does not exist. We are going to check it. But it does exist if you have something like x squared over x squared plus y squared, which is less than 1. Or you may have y squared over x squared plus y squared. So just give you a hint over here for future. Okay, you have to look for these two. Note that. You have to look for that expression like x squared over x squared plus y squared is less than or equal to 1. And the other part, y squared over x squared plus y squared is less than or equal to 1. So both of them give you bounded functions and enable you to have the, to do the job. So we'll see it from time to time when things getting more interesting. Okay, question? No. What's going to be next? There is something very much interesting about this type of functions. So we have one more question to answer. The question is going to be, how are we going to define, how are we going to prove for this type of function that the limit does not exist? Okay, so let's go take this problem as well. And that will help you so much for the rest of the course. So I'm going to give you a question to answer. Question. Okay, the question directly in some of the problems from now on, you may have to, or you are going to be asked. They are going to ask you to prove this kind of a limit does not exist. So let's say I'm going to prove that the limit does not exist. So recall from calculus 1, or especially for the piecewise divine function, recall that. You see, for calculus 1, because you're dealing with the numbers, you're just doing the right and the left limits, remember? In calculus 1, you say that the limit of f of x goes to x0 does not exist. This is one way to do it, even only if. If you get two different directions, the limits would be different. Limit of f of x when x goes to x0 from the left is not equal to the limit of f of x goes to 0, x0 from the right. Okay, this is the way you proved that the limit does not exist in calculus. Okay, a function of one variable. So in fact, what you do is, you see this is the number line. This is going to be a number line from negative infinity to positive infinity. And you have these points to find the limit at these points, x0. Okay, you know that you don't care about the x0, but so you pick two different directions. So you get the x's getting closer and closer to the x from the left and getting closer from the right. If these two numbers are going to be different, so in that case, the limit does not exist. And you know that if these two happen to be the same, in that case, the limit does exist. So the question is going to be, okay, the question is going to be, are we going to have a similar one or something similar for the function of, okay, so the question is going to be, are you going to have something similar for a function of two variables, f of x, y, x is 0 and y 0. I'm sorry, when x and the y goes to x0, y0. So, you know, you want to prove that this is does not exist, for example. If you want to check this one, so what's going to be the similar theorem that you can have over here? Okay, so the situation is going to be, you are going to have a point rather than the x0. So this is a situation you're going to have. You see your fixed point is going to be x0, y0. So this is going to be, okay, this is going to be your point. This is x0, and this is going to be y0. Okay, and the point is going to be what? This point is going to be x0 and the y0. So if you want to do the similar thing over there, so you have to find the two different values for your function, for your limits, when you pick two different direction over here. So let's see what would be this direction in two-dimensional that you are going to have. Okay, so what we do is, you know that it's going to be 1 point. So if you pick another point which is going to be close to the x0, y0, okay, so if I take something which is going to be close, so where I can take those points to be close to the x0, y0. Okay, so if I pick, just think about it. So if I can pick a point which is going to be close to this one, so what can I do? I can move a little bit to the right, to the left. Okay, so if I pick something, you know, if I pick something here, okay, if we pick something over here, so that would be, you know, the point like, okay, the point like x comma y. So then x, y0 goes to the, you know, goes to the x, y, getting closer and closer to the x0 and y0. So this means if I pick it over here, so as you can see, this is going to be the same x. So this is going to be the same x, but I just change the y, if you like. So the new point is I have the x0 and the, okay, another one, like, okay, what's that? Like the y. So the original one, I have x0 and y0. So I get the x0, y, and x0 and y0. So basically this means there are different directions that I can get closer and closer to these points. One direction is I can fix the x0. So it's just going from, you see, in this case, x is a fixed one, but the y goes to y0. This is one direction. I can find the limits. Then I can change the direction to the other side. Okay, the other direction is I can keep a y equal to the y0, fix it. Then I change the x goes to the x0. So there are different directions that I can go from one point to the other point. You see, this is going to be one point that I have, x0, y0. And I can come to this point from this direction. This is another one. So there are different ways that I can go from one point to the other one. You see, I can come in this direction. I can come in this direction. I can come in this direction. I can come in this direction, this direction, this direction. So this means if I want to prove that this limit does not exist, I have to pick two different directions, getting closer and closer to the x0 and y0, and arrive at two different numbers. If I arrive at two different numbers, in that case, the limit of the function does not exist. Okay, so basically, And this is, let me write down as a theorem, then I come back and explain it again. So the direction that you pick on the function of one variable is always along the x-axis. But if you are going to be in two-dimensional, you have different places, different way, you know. For example, if you want to go San Diego from Oceanside, so you have two different, okay? So you have various directions. It's not going to be just a unique path if you like to go through it. But if the limit exists, it doesn't matter which path are going to pick. You see this theorem? Let me write it down, then we explain it. That's a crucial theorem for you to be able to check the limits, especially when you want to find the limit does not exist. So I write it down in two different formats. The theorem, the first part. This the part is very bad. You made a mistake on this one. So if the limit, as you say, if the limit does exist, if the limit of f of x comma y, when x and y goes to x0, is like the right and the left limit that we have. If this limit is equal to the L, okay, if this limit is going to be equal to the L when x and the y go x to 0, y0, you see, then this limit would stay the same. Then we say that, okay, then f of x comma y goes to L whenever, definition of a limit, okay, whenever x, y, the point, goes to x0, y0, along any direction, along any smooth curve between, okay, between the points, x comma y and x0 and y0. That's it. It's like when you say the limit exists if and only if the right and the left limit exists in the function of one variable. But since it's a two-dimensional, so it doesn't matter in any direction. So from one point, at any direction that you're getting closer to the x0, y0, your limit must stay the same, okay? So this is again 1 point, x0, y0, and you're coming towards this point, you see, and this is another point. So it doesn't matter which direction are going to come, you see. And this is going to be one direction. Okay, you may pick another direction, various direction at any format. At any format that you pick, okay, this limit stay the same. So we usually go the direction in terms of the, this is in terms of the, okay, towards the x-axis, y-axis. So if you consider the origin, you see it's going to be the origin. So you have different possibility. You can come from this side, 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 or other various points. You can come from this side. Okay, it doesn't matter. All the time when you find the value of the function, getting closer and closer to the L. Okay, so if the limit does exist, then the limit would be unchanged if you pick different directions. That's the case one. Any question? Now your mistake is going to be, most of the people, they make this mistake on the test and you lose quite a lot. You should look at the statement of the theorem. If the limit does exist, then at various directions, the limit is the same. So forget about this one. If you want to, some people, they try to apply this theorem to prove that the limit of the function does exist, which is impossible. Because if you want to prove it, you have to consider all the possible directions, So it's good only if you want to prove theorems. It's no good if you be given a specific problem. Because if you be given a specific problem, it's not possible for you to find all the directions, okay? So forget about it for a specific function. But the way we are going to use it is this one. Like the one that I discussed. We are going to use it to prove that the limit does not exist. You see, like the right and the left limits. In order to prove that this limit does not exist, you must find two different directions. Two different directions for which the limit would be two different numbers, like the right and the left that you pick. Two different directions. If you find two different directions with two different numbers, then the limit doesn't. This is the way we use this theorem. So use it only when you want to prove that the limit does not exist. So the second part is this: if f of x comma y, or the limit, goes to something like, we call it L1, whenever you pick this direction, x comma y goes to the x0, y0 along the specific curve, okay, along a curve C1. So again, you want to go from Oceanside to San Diego, you go through the 5. This is the 5, and they get the L1. But if you change the direction, if you go through the I-15, so the second part is going to be, if this is going to be the case, L1, and again, f of x comma y, you go different direction, different path. This time it's going to be L2 if you change the direction. It's going to be L2 again whenever x comma y goes to x0, y0, this time along the I-15, along a curve C2. Okay, two different directions, two different numbers, of course. Okay, and L1 happen to be not equal to the L2. Like that, the right and left limits, they're going to be different, okay? So in two different directions, we get two different numbers. So according to the first part, this means the limit doesn't exist. Okay, then the limit of f of x comma y when x, y goes to x0, y0 does not exist. This is extension of whatever I studied, and that's going to be a great one that we're going to use. Okay, so this is it. This is the xy, and this is the x0, y0. Two different directions. You see, you pick this direction, you pick this direction, okay? This is the C1, you get the L1. But if you change another one, direction is C2, and the number is L2. Okay, so this basically L1 is not equal to the L2. So this means the limit does not exist. It's a great tool, and you are going to use it for the next 2 weeks. Makes things so easy for you. So this is a kind of a replacement for the right and the left limits that you use in calculus, a function of one variables, okay? So we have various direction because the function is the function of two variables, and you're moving, you can move it in 3-dimensional in space. So if you pick two different directions and you investigate the value of the function to find, when the point getting closer and closer, so you are going to get the limit. But if in two different directions you get two different numbers, the limit does not exist, okay? Not try to avoid this one, because this will tell you that if the limit does exist, then the limit at different directions are going to be the same, which is no good if the problem is given to you. You cannot use this one to prove the limit, okay? Because it's impossible for you. It's impossible for you to pick, to prove it for all the directions. But it's very much possible for you to reject it. Two different directions, you are going to see it, the way we are going to operate with this type of limits. Quickly, the direction is going to be famous, and be able to, to take care of it right away. Any question? Now let's see how we're going to operate. Okay, you see it in the case of the limit. Directly, there are a group of problems in your book that directly ask you to prove that the limit does not exist, and you will see, one of them on this quiz that we're going to have. Okay, so let's see. So pay attention to these examples, give you the method that we're going to use. So you see everything we do step by step is just reviewing calculus 1. So we're reviewing calculus 1, but at any point you may have to modify it. You may be able to use a similar one. So that give you the chance, okay, to to flashback in this idea from calculus 1. So that give you a better understanding. This shows that you did understand that concept in the function of one variable. Now we're going to extend it for the two variable. Okay. Not a special name for it. Okay, just property of the limit. No, we don't have any name. We usually refer to it, this is just a straightforward directions. We say check the limits for different directions. Remember, use it when you want to prove the limit does not exist. Don't miss it for the, okay, for the test. This part is good when we want to prove the theorems. So let's see how we're going to operate. There are kind of 3 types of problems. You will see all the 3 in your coming quiz and then in the test. And most of the time, we are going to use it through this chapter. Okay. So, I'll give you one remark. Most of the time, these limits would be asked when it's a 0, 0. So I give you all the direction for the 0, 0, because we are not going to use it, okay, for any other points. So they ask for the limit at 0, 0. So use these different directions that I'm going to give you, okay? So there you are. Note that it's our famous direction. Note that if x, comma, y goes to 0, 0, they usually give you this. So you want to go through this, okay, getting closer and closer to the origin. So what's going to be the possibilities? The paths. So these are the possibilities. These are suggestions, and most of the time it works. Okay, the following paths or curves are useful. So my suggestion is use this following. Okay, this is going to be the one. So let's see what you have your situation. So you get this one. This is the situation that you have. So you want to go through the, get closer and closer to the origin. The origin is going to be what? The origin is going to be 0, 0. 0, 0. Different way that you can get to the origin. Okay. Different way that you can go to the origin is along the x-axis, along the y-axis. You see, if you want to pick a point on the x-axis, you know that if you pick on the x-axis, there is no y. So this point is going to be x, comma 0. This is going to be along the x-axis. So if you go from this direction, x getting to the 0, 0. So this is the first one, the first path that we're going to consider is going to be the first path. So a path along the x-axis. If you're going to be along the x-axis, this means in this case y is equal to the 0. Y is equal to the 0. Okay, and x goes to x goes to 0. So this means you go to your function, you replace the y by 0, then y would disappear. You find the limit when x goes to 0. Okay, so this is the way we're going to write it down. This is the way we write it down. We say x goes to 0, but y is 0. So that's going to be the path along the x-axis. Okay, I'm going to use it in a minute. You will see it. If you did the other way around, if you want to come from the y-axis, so you have to pick this point on the y-axis. If you click on the y-axis, x must be fixed as 0. Then you have to pick the y. So in this case, it's going to be a path along the y-axis. So a y-axis means your y goes to 0 this time, and you keep the x to be constant. Okay, all of them means x and the y going to the, okay, getting closer and closer to the 0, 0. So you go to the 0, 0 along the y-axis. So you go to the function, you replace by x by 0, and you let y goes to 0. If you get two different numbers, you say the limit does not exist. And most of the time, this is going to be the case. Okay, that's the second path. The third path, if you are not done, if you cannot find two different numbers, you're going to pick the third one. What's going to be the third one? Look at this one. I want to get to 0, 0. So the third one is along this line. You see this line is a line y equal to the x. So in this case, you go to the function and you replace x or y, you let them to equal to each other, and then you let x goes to 0 or y to 0, doesn't matter. So this is going to be a path. It's going to be a path through the origin. Okay, a path along. Okay, along the line y equal to the x. So this means you go to your function, replace y equal to the x, and replace x by 0 or y by 0. So we usually say x goes to 0, but replace y by x. So we replace y by x, everything would be a function of x. Replace, then you let x goes to 0. If you get two different, so you already got these. So if you get a number which is going to be different from, okay, the first case and the second case, then you can say that the limit does not exist. Any question? There is another case that you apply these three, they are going to be all the same. So you have to change it. So you have to change something else going through the origin. The next one is going to be a curve type, kind of a parabola. You see, look at this one. If you get a parabola, so you can start with the point at the parabola and then getting closer and closer to the 0 in this case. So if it's going to be parabola y equal to the x squared, so this is another possibility. There is a group of them, and you have to use this one. So a path along the curve. Okay, most of the time y equal to the x squared, but or any power of x, or y equal to the x to the n, depends. You wanted to go through the origin, you may have the x cube, x to the 4, depends on the shape of the problem. And most of the time y equal to the x squared would be fine, but we can do it. So we replace the y by x squared. So in that case, again, x goes to 0, but y would be equal to the, what would be equal to the x squared, or one of these. So it depends on the given problem. You are going to pick the correct one. So almost all the problems that we are going to be given, and we want to check the non-existence of the limit of the function, are going to be around the origin 0, 0. So these are going to be the one that we're going to, we suggest. There is one more method in most of the calculus book. I've seen it. So they use x to the n for all of them. They decide, no, just be specific. Be specific because we need specifically two different numbers, L1 and L2. Everything must be precise. Okay, now any question? Now let's practice to understand what I'm talking about. So that if you that's it. You don't need anything else to take care of the limits really. Okay, that is, and quickly we can talk about continuity and then be done. Okay, so a set of problems. So we give one question, it's usually 3 parts, and we want to check the limit does not exist. And it's going to be given at 0, 0. Anything else can be changed into the 0, 0. So that's why they focus on the 0, 0. Okay, are you ready? So we never ask you to use these for the positive answers because it's not possible. So it's always used when you want to have a negative answer. You want to prove that the limit does not exist. Don't use it. Again, I repeat it. Because I've seen some people, they use it. If you use it, if the problem would have 10 points, you lose all the 10 points because you didn't use the, the proper, because it doesn't give you the result. It's not valid. Okay, are you ready? Example. That's it. Prove this limit does not exist. Show that. This would replace the right and the left limits on this method in function of one variable. Show that the limit does not exist. Show that the limit. Okay, limit of this function does not exist. That's it, does not exist. Or simply, this is the way we're going to do it. Does not exist. So this means you have to pick 2 different directions with 2 different numbers. Okay, all the popular ones are here. The first one. Limit of xy, x squared plus y squared, x comma y goes to 0, 0. That's the first one. You see, if you substitute, it's going to be 0, 0. But you can't find those ideas that I talk about it. Because x over x squared plus y squared, you don't have any information about it. Besides, does not exist. So pick 2 different directions. First direction, you fix the y. Fix means y goes equal to the 0. You let x goes to 0. That's one direction. The other direction, you fix the x, replace x by 0, y goes to 0 to see if you get the same answer. And you have to give us the details of this idea. Okay, solution. That's it. So direction, the first one, limit of x, y, x squared, y squared. So we can say that x goes to 0, and you fix the y to be equal to the 0. Okay, this is along what? It's along the x-axis. You substitute y first. So that gives you limit of x goes to 0. Okay, I explain it. Substitution x times 0. That gives you x squared plus 0. So we continue with the top. Limit of x times 0 would be 0. That gives you x squared. X goes to 0. Any question? Now, since x goes to 0, you know that x goes to 0 means x is not equal to 0. Since x is not equal to the 0, 0 over x squared would be 0. Okay, I just explained it for you. X is not equal to the 0. So it's going to be limit of the 0. Limit of the 0 when x goes to 0 is 0. That's it. So the limit of the function xy, x squared plus y squared. In the case x goes to 0 and y goes to 0. You don't have to rewrite by rewrite. This is case 1. Any question? So be precise on the test. You see some people, they make a mistake. This is the way they talk about it. They say x goes to 0 is going to be 0, 0. No. When x goes to 0, you see x is not equal to the 0. When x is not, before taking the limit, you see before taking the limits, this is 0. Because when you're taking the limit, x goes to 0, remember you estimated x is not 0. So this would be 0 and the limit of the 0 is 0. Again, some people on the test, they write this is equal to the 0 over x squared, then 0. We give you 0 right away. Doesn't make sense. Limit, 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 limit. If you don't point the limit here, it doesn't make sense. Okay, limit, limit, limit. So we usually drop this part. We say limit of x squared, limit of 0 over x squared 0. We accept it right away. Any question? Second direction. You need two different directions. Second direction, fix the x. Limit of, okay, then it's going to be x, y. It can be done, into a few seconds, usually on the test pad. So we let y go to the 0. We fix the x. Replace x by 0 first, going to be limit of, and just do it, but later we make it short. It's going to be 0 times y, and it's going to be 0 plus y squared. Only y goes to 0. Again, the top would be 0. Okay, 0. The bottom one would be y squared. Y goes to 0. Before taking the limit, it's already 0. So it's a limit of the 0. And the y goes to 0, which is equal to the 0. That's it. No good. Okay, it's no good. Some people, they make a mistake. They try to say that, oh, the limit is 0. No. You are going to prove this limit does not exist. So you have to take another direction. Okay, any question? So usually you will see when I do the second one, we just check it before writing it down. In this case, I want you to see it. So we need, okay. So along the y-axis, along the x-axis, so go to the other direction, the direction of going through the origin, okay? So we need the third one. So be prepared. The third one, xy, x squared plus y squared. Remember, x goes to 0, but you let y to be equal to the x. So we go through the origin through the line y equal to the x, okay? So that was, that this is, don't need to explain it. This is along the x-axis, okay? So that was along just for your information, x-axis. So this is along the y-axis. So it's no good. We have to continue. So replace y by x first. So that gives you the limit of, it's x times x. And this is going to be x squared plus x squared. Keep up, simplify. The top would be the limit of x squared. The bottom one would be 2x squared. X goes to 0. Again, x goes to 0 means x is not equal to the 0. So we can simplify the x squared and the x squared so that you 1/2. It's going to be limit of 1/2. X goes to 0, which is 1/2, which is a good one. Okay, it's good one because you have two different numbers. 1/2 is not equal to the 0. Okay, so you find two different directions. Two different directions with two different numbers. So according to that theorem, the result is that the limit does not exist. Therefore, the limit of xy over x squared plus y squared, x comma y goes to 0, 0, does not exist. And you done. Of course, we make it short. You will see how I do the next one. Then that give you the idea. Any question? So it's a very nice method, and that enable us to, to take care of these. And when the problem is given to you, really, you just check it before just applying. Look at this one. When the problem is given right at the beginning, you just check it yourself. You say, oh, if I change x to the 0, the top would be 0, so this is 0. If I replace y by 0, the top is 0, that gives me 0. So I won't get anything. So I go to the third. I replace x by y, that gives me x squared plus x squared. So it's x squared over 2x squared 1/2. then they are not. Okay, this is the way you can check it, but you have to write the two cases that you show. You don't have to check all of them. Just give us the one that you enable you to get the result. Okay, any question? That's the first one. So a couple of them. So this is our main tool. Just to make sure you understand it and the way you write it down. Okay, so I get the second one. I show you how you write it down briefly. So they are very famous or popular examples, problems, so they're not going to be much different between. There is one tricky one between this group. Other one is going to be straightforward. Okay, xy goes to 0, 0. You want to prove that this limit does not exist? Give a few seconds. Just think about it. Which directions? Or if you have a solution. Check your directions along the x-axis, along the y-axis to see if you can see, or if you need the third direction. Okay, do you have anything? Anybody make a comment on this one? Which directions and with the numbers? Direction and your numbers. Let's see. Okay, Patrick, y equal to the x squared. So what's the second direction? You need two different directions. Two different directions to get two different numbers. Kelly, along the x and the y, yes. Along the x and the y would give you the numbers 1 and -1. Yes, you're right, thank you. You see, we check the x and the y first. Just have a look. You fix the y, we replace the y by 0. So if you replace y by 0, that would disappear. X squared over x squared, that give you 1. That's one direction. If you fix the x, replace the x by 0, that gives you 0, 0. Negative y squared over y squared, that gives you -1. So positive -1, done. So we don't need any third direction, okay? So you can check it yourself first, but you have to write it down for us. So there you are, the direction of the x and the y first, okay? X-axis and the y-axis. So I go with x goes to 0, but I fix the y. So this give me what? X squared minus 0, x squared plus 0. So that give me limit of x squared over x squared. X goes to 0, which is limit of 1. And limit of a constant is just 1. This is the way you write it down. Any question? That's the one direction. The other one, limit of, this time y goes to 0, fix the x. This is along the y-axis. So you substitute x equal to the 0, that gives you 0. Okay, that gives you 0 minus y squared, 0 plus y squared. So that gives you the limit of a negative y squared over y squared. Okay, x goes to, y goes to 0. You simplify it first. That gives a limit of a -1. Y goes to 0, and the limit of a constant number is constant. There you are. So we have two different numbers. Y is not equal to the -1, and the limit does not exist. Limit of x squared minus y squared, x squared plus y squared, x comma y goes to 0, 0. does not exist. Very good, excellent. Any question? So this is, the way you pick and you talk about it. This problem is in your book, but they changed it a little bit. Let's check that one too, to see the difference. You see, this is one of the problem in your property assignment. Limit of x squared minus y squared over x squared plus y squared. Everything is square. Similar. So how about this one? Which direction would give you your answer for this? Check your direction to see which one is going to be appropriate for this one to get to arrive at the two different numbers. Let's see, we have a suggestion. Okay, Kelly, along the x-axis and y equal to the x. Yes, that's correct. You see the first and the second direction, as we did it for the other part, give you the same number. Quickly, you check it first for yourself. You see replace y by 0. That give you x squared over x squared, which is 1. You square it, you get 1. If you replace x by 0, that give you negative y squared, or y squared, that give you negative 1, but you square it. So that give you positive 1. So it's no good. You can get only x1. So you need the third one. The third one will go along the y equal to the x, that line. You replace y by x. So that give you x squared minus x squared, but give you x squared plus x squared. So that give you 0. So that give you the third direction. Okay, so you have to do, so you don't have to write the x and the y, just one of them. You pick either one is fine. So for example, I'll go with this one. I let x goes to 0 along the x-axis, y would be 0. So a substitute, get the y equal to the 0. So that give me 0, that give me x squared plus 0. And this is going to be a squared. Okay, so this is going to be equal to the limit of, so I get the x squared over x squared all squared, and then x goes to 0, but you simplify it first. You simplify that, give you 1. So that give a limit of 1. X goes to 0, which is equal to 1. Okay, so that's the one direction. So you already, check that and find out that if you take the y-axis, won't give you the result. So you change the direction, you go to the y equal to the x, y equal to the x squared, depends. So we go to the x goes to 0, but we replace the y by x. Okay, you don't have to write the other one. So we need one of them, x or the y-axis. Okay, go back, replace the y by x. So it's going to be x squared minus x squared. That's the x squared plus x squared, all squared. You see the top would be 0. So this is going to be the limit of 0 on the top, 2x squared on the bottom, all squared. Since x goes to 0, you see x is not equal to the 0. So this would be 0. So the limit of the 0 when x goes to 0, which is equal to the 0, two different number. Y not equal to the 0, so the limit does not exist. See, it would be after a while, you get used to it to see how you're going to operate with this type of problems. But you have to check to see what's going to be So this does not exist because we skip through direction. Okay, so let's have a break. And we need one more. The last one is tricky. The one it's otherwise we don't have any other cases. And the way you're going to pick that that function is going to be a little bit different, and then you will find. Okay, any question? So let's have a break. It's at 12:03, so I give you 12 minutes. So we come back at 12:15 and to continue to take care of it. We are done almost with the limits. We're done with the limits. Quickly we can take care of the continuity and finish this section 13.2. It's a very long section. Okay, see you then. Okay. So we were just working on these examples. Okay, limit does not exist. So there is going to be a third case. So just give you that third one. Okay. This one is different. You see, for the other one that you did, mostly they are kind of called homogeneous. The power of the x squared and the y squared, you see, they are all like the same as each other. When you substitute different direction, it can be simplified easily. But this next one, the powers are different. So that is going to be number 4. There's not going to be any other possibilities, okay? So there are different versions of this problem. So this is one of them that we're going to have. So the limit of x, y squared. Okay, xy squared, and we get the x squared plus y to the 4th. And then this is going to be where x comma y goes to 0, 0. Okay, let's see what's going to be the difference between this one and the other one. Quickly, we check to see if the direction would give us something. So if you replace the y by 0 and fix the x, replace y by 0, that give the top would be 0. The bottom one would be x squared, so the result would be 0. So this is one direction. And if you replace x by 0, you get the x0, so the top would be 0. The bottom of the y to 4, that gives you 0. So the direction of the x and the y give you the same number. So you need a third direction to be able to do it. So for the third direction, we usually go with the y equal to the x. If you go y equal to the x, the difficulty is going to be that would be x squared, that give you x cubed on the top. And that give you x squared plus x to the 4th. So you are not going to be able to simplify it to get the result. You can simplify because you don't need 0. You do need a fixed number, a non-zero number. So you have to take a power of the x or power of the y, doesn't matter. So that the term on the top, you see those monomials are going to be all the same. So that would enable you to simplify it, okay, with a fixed number. So you have to think about it. Which power of the y or which power of the x. You see, if you look at the denominator here, you see, for example, the power of the x is lower, x squared, and the power of the y is higher. So if you want to pick something for the y to make it to the x squared, you have to pick the lower power. Okay, or you can do it the other way around. So let's see what are we going to do. So pick one direction to get the first one along the x and the y axis, go x to 0 and the y 0. So in this case, this is it. See, the top would be 0. If you substitute the y equal to the 0, the top would be 0. And this is going to be x squared plus 0. So the result would be the limit of 0 over x squared. When x goes to 0, y disappear. And this limit quotient of the 0 over x squared is already 0. So when x goes to 0, that gives you 0, 2. So that gives you one direction. Okay, direction of the x equal to 0 is no good. So you have to pick another direction. Any suggestion? So you have to pick something through the origin. To just you have to pick something so that you'll be able to match the powers that you have. Then you'll be able to simplify it to get, to get a fixed number. Y equal to 1 or x equal to. Just think about the powers of the y or the power of the x that they give you the same thing that you'll be able to simplify it. Any suggestion? This is x squared. So if you get the x squared here, then you can simplify it. So y equal to what? Let's see. Patrick, you're right. Yes. That give you radical x. Yeah, radical x, square root of x is a good one. You see, the direction they're going to pick it is, this is it. You have to pick, pick power of the x, replace for y, so that give you x squared here. So if you let y to the fourth to be equal to the x squared, y would be radical x. So that's one option. The other option is you can match the power of the y. You can pick x to be y squared. If you pick x to be y squared, that gives you the y. So two different choices. So one choice is if you replace x goes to 0, but replace y by radical x. Okay, so this is it. This is x, and that gives you radical x squared. So that would be x squared, and that would be radical x to the fourth. Okay, so it's going to be equal to the limit of your x goes to 0. You simplify the top. Okay, so that gives you x times x, radical x squared. And this is going to be x squared. Radical x to the fourth would be x squared again. And so that's it. The top would be x squared. And the bottom one is going to be 2x squared. 2x squared, x goes to 0. You simplify the x squared and x squared. So that gives you 1/2. So the limit of the 1/2, when x goes to 0, the result would be 1/2. Okay, so you get two different directions, two different numbers. So this means the limit does not exist. So this is another case that they give you two different powers, if you like, of the x and the y, and then you'll be able to take care of it. Any question? Second option is they're going to be, you see, option 2. Option 2 is you just pick the, okay, you let y equal to 0, and you pick x to be y squared. See, I want to match this power. You see, if you want to raise the power of the x to make it to the y to the fourth, you need the y to the fourth, so you get x equal to the y squared. It's going to be the same thing. And replace x by y squared, so that give you y squared, and the bottom one that give you y squared plus y to the fourth. So you're going to have a y to the fourth on the top, and that would be y to the fourth plus y to the fourth. Y goes to the 0. So this is going to be limit of y to the fourth, 2y4, and the result would be 1/2. Okay, it's another option. Then we get the 1/2 equal to 1/2. That's one. In your book, you have x. I think you have x squared plus y to the 6 in your assignments. You have quite a lot in your book. You have one section all through list of all these problems together. Your book is very good in this, in this part, the Larson book. But you will see all of them in your next practice quiz, all the possibilities. That's it. This is the limit of a function of 2 variables. That's the one. We can do the same thing with the function of 3 variables. Okay, and we are going to give a couple of examples later. Any question? So get to know this method. It's very crucial for you, okay, for the examples that we're going to have, and we are going to use it later on as well. So there are some times that you may limit what we given to the ask, find the limit if it exists. If it exists means either it's going to be of this form, you're going to reject it, or it's going to be the form that I talk about it, that use those bounded function. Otherwise, it's going to be just straightforward, and we are going to practice it tomorrow again. Okay, so that is the limit of the function of the 2 variables. As soon as we get the limit, of course, continuity. Okay, again, part of this section. A continuous function is going to be the same as you did before. You know that the limit is an estimate of the value of the function, but in the case of the continuity is a precise value. So if the limit of the function and the precise value of the function happen to be the same, the function is continuous. So nothing is changed. Everything is going to be the same as a function of one variable. So we have to make it official, okay, to get these numbers. Any question? So the last topic of this section eventually is going to be continuity. Right, there are a couple of interesting examples over here too. So 13.2, it's part of 13.2, just for emphasize on this. So continuity. Okay, but it's going to be continuity of a function of several variables. Of functions of several. Okay, the function of several variables. So we check this one. That's it. The function must be defined at a point, and then you get the continuity notation. So just the definition is going to be the same thing. So a function f of x comma y, I make it brief because we know everything about this concept. Okay, it's going to be continuous. Is continuous at the point continuous at the point x0 comma y0 if the limit of the function, limit of f of x comma y, when x comma y goes to x0, y0, it's equal to the value of the function f of x0 comma y0. Okay, this is a continuous function. And as usual, a function is continuous on the domain if it's continuous at any points on that domain. So a function, because you have to find the domain of the continuity for us. A function f is going to be continuous. Going to be continuous on the domain. Continuous on the domain D in R2. Now the domain is subset of R2 if it's continuous at every point. If f is going to be continuous, it's going to be continuous at any point. Continuous at any point in D. Same thing. So we don't have to repeat the theorems that we know it because again, we already talked about the limits because the range of these functions are real numbers. So the same situation that we did have in function of one variable are going to be satisfying. For example, if two functions are going to be continuous, since the range are real numbers, so it makes sense to talk about the sum of the function, the product, okay, the quotient, etc. They are all continuous. And as usual, a polynomial function, okay, a polynomial function in two variables are going to be continuous. So we have everything we did before nicely. So your job is only, we give you a class group of these functions, and we ask you to check whether this function is continuous or not. Okay, just use the theorems that like the one that you did before. Okay, that's it. So example, we don't have anything different at this level. And we give you one question on this. Okay, a group of function would be given. There are going to be two types of function, like in calculus 1. Is a kind of a polynomial types or the rational function of the polynomials. And then, of course, a piecewise defined function, which are very much going to be of our interest. Okay, there you are. So determine, okay, determine where the function is continuous. Where the function is going to be continuous. That's it. As usual, the first one is going to be polynomial type. F of x, y is equal to x squared plus 5xy minus y cubed. You know that restriction would comes when it's it's not going to be a square root. It's going to be rational function. Otherwise, it's a polynomial function. It's a polynomial function, so it's continuous everywhere on the domain. The domain is R2. So it's going to be continuous for all points. Okay. So make sure when you give us the set of continuity, the domain of these functions are collection of points. Don't say it's continuous for every real number. That doesn't make sense. It's continuous for every point because of the domain. Okay, so otherwise it's don't have to worry about it. Okay, so we mentioned that f is a polynomial. F is a polynomial function and is continuous. And is going to be continuous on its domain, R2. Continuous everywhere in R2. Question? So this is the way we're going to take this one. So that will take care of polynomial types. Ready for the next one? Rational function. Number 2, f of x, comma, y is equal to, the top would be x minus 2y. And the bottom one is x squared plus y squared. Rational function. Okay, the top is a polynomial, the bottom is a polynomial. So the quotient, the polynomials are continuous, so the quotient of continuous function continuous. But you got to be careful, remember, it's not going to be continuous when the denominator is equal to the 0. So you let the denominator equal to 0 to see what is wrong with that case, okay? So as with the function of one variable. So this is how we're going to explain it. F is going to be continuous. Okay, F is continuous. Okay, it's going to be continuous everywhere. On R2, there, of course, or when x squared plus y squared is not equal to the 0. And you have to tell us, so note that if they are going to be 0, if x squared plus y squared equal to the 0, because they are non-negative numbers. So this means in that case, x is equal to the 0 and y is equal to the 0. So this function is continuous everywhere except at the origin. Okay, so f is continuous. F is not continuous. Continuous at 0, 0. So in short, the conclusion is going to be f is continuous. F is continuous. It's the way we write it down. On R2 minus 1 point, the origin. This is the notation that we use. Okay, so this means every point except 0. So where is the rational function? You have to exclude. Remember, again, it's a function of one variable. You have to exclude the zeros of the denominator. So this denominator would be 0 at 0, 0. So the function is going to be continuous everywhere except at the origin. Any question? So this is the way you answer it, this type of problems. Give you another one. Just make sure you know the way you express it is going to be mathematically sounded. So let's see what's going to be the next one. Number 3. Number 3 is this function. G of x comma y is going to be equal to 2 over y minus x squared. Rational function. Everything nice, top, nice, continuous. The bottom one polynomial y minus x squared continuous. But again, this function is not going to be continuous. It's continuous everywhere except when the denominator is going to be equal to 0. Denominator would be 0 if y is equal to the x squared, which is a parabola. So this means this function is continuous everywhere except for the points that are going to be on that parabola. So this is the way you explain it. Solution. G is continuous. G is continuous. Again, everywhere. Okay, it's going to be continuous everywhere on R2, except, of course, except except all points that are going to be on that parabola. All points that are on the parabola y equal to the x squared. Because if the denominator is 0, you know that this function is going to be undefined. So that's one way to write it down, or if you like, in set notation, you can say that G is continuous. In short, it's going to be continuous on the collection of all points x and y that satisfy this condition, y not equal to the x squared. That's in short. Short, and you know, this makes sense. So this function is continuous because your collection is going to be collection of points in our two-dimensional. Okay, and the condition is that the denominator cannot be 0, so y cannot be equal to the x squared. You know, we accept both of them, whichever you know you're right. Any question? So again, that gives you, the chance to see how you're going to express the continuity or the domain of these functions. Now we are going to take one function of 3 variables. It's the same thing, but to know that it can be done. So another one is f of x, y, z, function of 3 variables, and this is going to be equal to the x divided by 9. It's a very popular case, 9x squared minus y squared minus z squared. So you want to check the continuity of this one. You know that this function, the top is a polynomial, it's continuous. The bottom one is continuous. Of course, there is a restriction. It's a square root. So that the square root function is continuous if the denominator, if the inside of the radical is not a negative number. So that will give us the restriction for the continuity. Okay, so this is the way we're going to write it down. Again, you are going to focus on the fact that f is continuous. Remember, your domain is going to be a subset of R3 because you are in three-dimensional. Okay, so f is continuous. F is going to be continuous. Continuous on everywhere, okay, or on all points in R3 or points X, Y, Z in R3 that satisfy this condition such that inside the radical is not a negative number, such that 9 minus x squared minus y squared minus z squared is strictly bigger than 0. You know that for the radical function bigger than equal to 0, greater than equal to 0 would be fine. But since it's done the denominator at the same time, okay, you have to make sure that in that case, okay, make sure that the number is not negative. So we can move this one to the other side to see it. So it's going to be x squared plus y squared plus z squared, which is less than 9. So you know that. You can write down in there. This is x squared plus y squared z squared equal to the 9 is a sphere. So it's going to be points inside the sphere. Or write it down in, okay, in set notation, set form. F is continuous. F is going to be continuous on the collection of points X, Y, Z, with the condition that the x squared plus y squared plus z squared going to be less than 9. Okay, it's going to be all points inside the sphere of the radius 3. Okay, you don't have to, but if you like, all points inside. Okay, inside the sphere with radius 3. So we accept, either one. We just give us this one, we accept it, or just collection. The standard format is just that collection of points to write it down. Okay, for the function of 3 variables, this is going to be, a very popular case. Any question? So again, these are the extension of the real valued function that usually, we took care of in calculus 1. Now, the big one are going to be the next group. The next group, piecewise defined function. Okay, like you did for the function of one variable. You know that when it's a piecewise defined function, we have to worry about the partition points. And these are going to be a good one or very popular in the function of 2 variables. So let's check a couple of them. They give you one question on the next quiz. For the continuity, it's going to be 2 parts. The first part, one of these. The second part, of course, a piecewise defined function. And those piecewise defined functions are going to be a source of various counterexamples that we are going to have in this course. Okay, that's why we are going to check them. So number 5 is different. Piecewise defined function. So what's the function? The function is this one. And you want to see where this function is continuous. It's going to be f of xy is equal to, the first part is x squared minus y squared over x squared plus y squared, with the condition that the x and y is not equal to the 0, 0. You know that this function is not defined at 0, 0. And this is equal to the 0 at the origin when x, y is equal to the 0, 0. See, that's one. You see, domain of this function is R2. because you are going to be in two-dimensional, X and the Y, and it's always defined for both cases. So you focus on the domain first. Okay, this is it, solution. So first the domain. Note that domain of the function is R2. All the points. You see, to check the continuity is like again a function of one variable. For the function of one variable, we forget about this partition. We forget about the 0, 0. If you forget about the 0, 0, you see this function is continuous. We already talked about it. The top is continuous, the bottom is continuous. The quotient of continuous is continuous. Of course, the difficulty is 0, 0, so we don't consider that. So the first thing to do is this one. So this function is going to be continuous. It's a note that equal to the R2. And if you like, so far, and f is continuous. F is going to be continuous on what? On R2, but not the origin. Okay, that's so far. But you have to check the continuity at 0, 0. That's it, exactly. Every day we do it, a function of one variable. How going to check it? The function of one variable in calculus 1, remember we check the right and the left limits. Over here, in function of two variables, three variables, you know that we have to check the limits in different directions to see if at different directions get different numbers, you're done. And then the function is not going to be continuous at 0, 0, and this would stay the same. But if we can prove this is continuous, then it's going to be continuous everywhere. Okay, so exactly as we did for the function of one variable. We have to check only continuity at 0, 0. If this function is going to be continuous at 0, 0, so it's continuous everywhere on R2. Otherwise, it's continuous on all the points except 0, 0. Okay, so the result is going to be, we are going to check is f, just for information, continuous. Okay, is f continuous at 0, 0? At 0, 0. Okay, so you have to check the limit. So we check the limit of the function f of x comma y. These are just for information. You can do it short form. When y goes to 0, 0. Okay, you have to find this limit. You know that xy goes to 0, 0, x and y are not equal to 0. We use the first one. So we have to check this limit. Okay, if this limit does exist, then you can talk about the continuity. But first, try to see if you can reject it. Check direction. We did it before, so we can check the direction and you see it. Quickly, if you replace the y by 0, that gives x squared over x squared. The limit would be 1. If you replace x by 0, that gives negative y squared, and positive y squared, that gives me negative 1. So 1 is not equal to negative 1. The limit does not exist, and the function is not continuous. Okay, so your job is just checking those direction, and you prove it. You have to show it, So we say, okay, the limit of x goes to 0 and y is fixed at 0. Substitute. So that gives x squared minus 0. And then we get x squared plus 0. So that gives a limit of x squared over x squared. X goes to 0. And we know that. We simplify it, and that gives us 1. So that's one direction. Any question? Second direction, limit of y goes to 0. X to be fixed. Go back, substitute. So X is fixed at 0, so it's going to be 0 minus y squared. And that would be 0 plus y squared. So we arrive at the fact that the limit of y goes to 0. So the top negative y squared, the bottom one y squared. So we simplified, we get negative 1. That's it. 1 is not equal to negative 1. So the limit does not exist, and so the function is not continuous at 0, 0. Okay, so f is not continuous. Not continuous at 0, 0. So the result's going to be a stand as we talk about it at the beginning. So the conclusion, the conclusion is that f is continuous. F is going to be continuous. Okay, continuous on R2, but not the origin. So this is the way you are going to test the continuity of the piecewise defined function, and this is type 1. Any question? So as you can see, it's a very nice one. You just extend the notion of whatever you did in calculus 1, a function of one variable, and those right and the left limits replaced by the taking the limit at different directions. Okay, and different direction you get different numbers. So this means this function stay as is, continuous everywhere except at 0, 0. Okay, any question? That's a type 1. There are going to be 2 types. So let's check the type 2 already. What's going to be the type 2? Type 2 is interesting. That's going to be your challenge. Okay, to check this one. So that's going to be number 5, and this is different. Let's see what's going to be new about this one. Okay, let's see what's the function. This is your function, f of x, comma, y. Okay, so this is going to be equal to, it's equal to the 3x squared y divided by x squared plus y squared. Okay, and this is going to be the case when x comma y is not equal to the 0, 0. And this is going to be equal to the 0 when x comma y is equal to the 0, 0. Okay, so the function is partitioned at 0, 0. We just want to check to see what is going to be the continuity for this one. Okay. Again, we check. You see, when the x and the y is not going to be 0, 0, the function is nicely continuous. Because the top is continuous, the bottom is continuous, okay? The top and the bottom are going to be continuous over here. And so the denominator is not 0. Again, you have to check the continuity at 0, 0. Okay, so this is the way we're going to operate solution. So the domain of this function is going to be, okay, so the domain of the function is going to be R2 again. You see that is going to be the case, and f is so far, and f is continuous. Okay, and f is continuous so far on R2 minus the origin, minus 0, 0. That's so far. Again, the question is going to be, is f continuous? F continuous. Okay, it's going to be continuous at 0, 0. Okay, we check this. So for this one, we have to check the limit. Okay, so we have to check the fact that the limit of f of x, y, okay, x, y goes to 0, 0, which is equal to the limit of, okay, 3x squared y over x squared plus y squared when x goes 0, 0. So what do you have for this one? Okay, so you know, if you go with the direction, you know, because I extend the y around the top. So if you get x equal to 0, that gives you 0, y equal to 0 give you 0, y equal to the x, that gives you 0. All of them give you 0, 0 all the time. So you just check to see if there is a possibility that this limit does exist. Okay, and if it does exist, it must be equal to the 0. Just check to see if you can prove it by that idea that it is going to be a product of the, okay, the product of a bounded function and the other one. Look at this expression that we talk about it. You check to see if you can have, you see, x squared over x squared plus y squared. This portion is less than equal to 1. So you can use that kind of a squeeze type theorems that we talked about it before to prove that this limit is going to be equal to the 0. Okay, so that's the one that you have to note. So you note that, you see, I told you it's going to be x squared over x squared plus y squared, or the other way around. You see, you have this one this time. In the problems that given to you, either it's x squared on the top or it's y squared on the top. If you see these two, then you can modify it to prove that this limit is 0, but you have to explain it. Any question? So this is the way we are going to explain it now. You want to prove this limit is 0, so we estimate it. We say, oh, okay, note that. This is how you estimate it. The absolute value of 3x squared y divided by x squared plus y squared minus 0. You have to provide that inequality that we talk about it. So it's going to be equal to, so pull this 3y out. So that give it 3y times that by x squared over x squared plus y squared. You see that's 1. So it's going to be equal to the absolute value of the first one, absolute value of 3y. The second one, we don't need any absolute value because everything is positive. X squared plus y squared. But you know that this is less than 1. You see this one is less than equal to 1, so that make it into. So what we have is the fact that the absolute value of a 3x squared y over x squared plus y squared minus 0. Now it's going to be less than equal to the 3 times the absolute value of y. You have to explain this. Question? No, you can argue as we talk about it. You can say that, oh, okay, if x, start moving. If x comma y goes to 0, 0, okay, then you see, then y goes to 0. And when y goes to 0, then 3 times absolute value of y goes to 0. So 3x squared y over x squared plus y squared goes to 0 too. So this means that that limit, you don't have to prove it as I did it. Okay, I said for the math major, you know, you can go on connected, but that's okay. That's, you know, you have a precise proof. So the limit is 0. Limit of the 3x squared y over x squared plus y squared when x comma y goes to 0, 0 is equal to the 0. But this 0 is at the same time f of 0, 0. You see? the function is 0 at 0, 0. So this means this function is continuous at 0, 0. Okay, so this means f is also continuous, at 0, 0. So it's continuous at the partition point as well, so it's continuous everywhere. So the conclusion is that f is continuous everywhere on R2. F is continuous. Okay, it's going to be continuous on R2. Nice problem. Okay, so when it's a piecewise defined function, there are two possibilities. You may get a continuity for all the points in the domain, which is R2, or you may get all the points except the origin. And as I talk about it, for this case, just look for this quantity here. You should be able to, to bond this one. You have to put the restriction on it to be able to do it. And there are, just 2 cases only, and then you'll be able to do it. Any question? So compare them together, number 4 and number 5. For the continuity, there are going to be a couple of cases that we need a kind of a counterexample. We come back and we check this. And there are not going to be any other types really. Or the one that you have in your book, you just switch it and you get this one. Any question? So we need to give you one more of the continuity. We haven't talked a function of 3 variables. And again, you have a group of them in your book. So I have to give you one. Okay, this is going to be similar method, but to make sure you know how to handle those steps as well, then we finish this section 13.2, which is a very long section. Okay, are you ready? Taking the last example of the limits. This is also interesting. We see how you handle this 3-dimensional one when the domain is in R3. So that would be our last example of the continuity, number 6. So what's the function? You see, this is the function. F of x, comma y, comma z. Function of 3 variables. So the domain is in 3-dimensional. So this is going to be the function. The top is this. You have a similar one in your book. X times y, y times z, plus z times x, divided by x squared plus y squared plus z squared. Okay, and it's the case that the x, y, z is not equal to the 0, 0, 0. And it's going to be equal to the 0. Okay, it's equal to the 0 if x, y, z is at the origin. And it's a very popular example. Okay, you want to check the continuity of this one. Again, you have to consider 2 different cases. Remember, the domain is R3 in this case. Just remind ourselves, because it's 3 variables. Okay, so the domain of the function is R3. And if we consider, if you forget about 0, 0, this function is continuous. So top is a bunch of a polynomial function, the polynomial in 3 variables, and the bottom is the same. So again, your difficulty is going to be what will happen at 0, 0. So we said domain is R3 and f is continuous. So far, f is continuous. Okay, it's going to be continuous on everywhere, which is R3. Okay, minus the origin. 0, 0, 0. So that's the situation that we have. So we have to check to see if the function is continuous at 0, 0. Okay, so the question that we have is going to be is, okay, is f continuous? Is f going to be continuous at 0, 0, 0, 0, 0, 0? Again, this is equivalent to the fact that you check the limit. Okay, so the question is going to be, is this limit does exist? The limit of the function f of x, y, z, when x, y, z goes to 0, 0, 0, which is going to be the same as the limit of the first part. xy plus yz plus z times x, and you have the x squared plus y squared plus z squared. When x, y, z goes to 0, 0, 0. The question is going to be, is this limit exist? You want it to be 0, of course, to get the continuity at that point as well. Again, you have to try. Okay, you try to reject it. So you have the same thing that we did for the function of 2 variables. In this case, we have 3 variables. So, along the x-axis, y-axis, you can fix one of these variables or even 2 of these variables to get different directions. So to get the different directions and to get the different numbers. Any suggestion for this one? You can check a different direction. One direction is easy, you fix 2 of these variables and you let, for example, x goes to 0. You're going to be along the x-axis if you like. So if you check 1, you can check yourself. If you fix the y and the 0 to be 0, so the bottom one would be x squared. You fix the z and the y. So that would be 0, that would be 0, that would be 0. So the top would be 0 all. The bottom one would be x squared. You know that this would be 0. So in one direction, you are going to get the 0. We can write it down, even this one. Okay. So the limit of what I just let x goes to 0. Then we fix the other 2. We fix the y equal to the 0, z equal to the 0. Okay, if you put it on the top, as we talk about it, all of them would be 0. So on the top would be 0. And the bottom one, we have only x squared here. And everything else would be 0. So that will give us the limit of 0 on the top, x squared on the bottom, x goes to 0. You know that this limit is 0 before you take any action. I mean, the inside 0 over x squared would be 0, so that gives you 0. Okay, this is going to be in one direction. You need a second one to be a number which is not going to be equal to 0, and you have many possibilities. Any suggestion? You need a constant. Let's see what we have here. Okay, Angel, z equal to the x, y equal to the x. Yes, you are right. Very good. So we get so the suggestion is x goes to the 0 and replace the z and the y by x. You see, if you replace z and the y by x, so that gives x squared, x squared, x squared, make it to 3x squared. And on the top, you change everything to the x squared, x squared, x squared. Yes, you get a fixed number, and then you're done. Very good. Okay, so You have, various options and you need one of them. So the limit of x goes to 0, changing everything else to the x. So let the y be equal to the x and the z to be equal to the x. Okay, it's like x equal to the y equal to the z. So you just substitute on the top to see what we're going to have. You see the top. So it's going to be xx. That would be xx and the xx. And the bottom one would be x squared plus x squared plus x squared. Okay, then the top is going to be all x squared. So it's x squared, x squared, x squared. And the bottom one, 3x squared, x goes to 0. So as you can see, the top would be the same thing. 3x squared over 3x squared, x goes to 0. You simplify it, and that give you a limit of 1. Just 1, but I just explained, equal to the 1. That's it. Two different directions. 0 is not equal to 1. So this function is not continuous at the origin. Okay, so f is not continuous. Not continuous at the origin, at the 0, 0, 0. So the conclusion is that this function is continuous everywhere in a space except the origin. Okay, so the conclusion is f is continuous. Okay, f is going to be continuous on all the points in a space except the origin. This is the way you write it down. That give you the final answer. Okay, it's a collection of very nice examples, really. Study this carefully. You get quite a lot in your book, but just when you pick your assignments, pick something similar to this. And because the examples that are going to be in your book or any other calculus book, they are very similar. But we just want to make sure we understand the method or the way, just checking these directions. Remember, as you can see, I never use this directional one if I want to prove that the limit does exist, because it's not working. Only I use different directions when we want to reject it, because it's easy to find two directions with the two different numbers. If you want to prove it exists, then you have to check all the possibilities, which is impossible. And that's it. I think that would be enough for today. Eventually, we are done with this great section of the 13.2. So we're done with these new functions that we introduce. So we're done with the limit and the continuity of these functions. So the next step is going to be differentiability of this function. We are going to be in trouble for that one, because the concept of the differentiability is going to be very tricky. How we're going to handle the differentiability of these functions. There are different ways to do it. Easy way is if you want to get back to calculus 1. So if it's a function of two variables, we freeze one variable. Freeze means you consider y to be constant. If y to be constant, your function is a function of x, you differentiate it. Then you come back, freeze x, differentiable. These derivatives are going to be called partial derivatives. They're all possible. So we start with the partial derivatives and we'll be fine to do most of the problems. But eventually you have to handle the derivatives. So for the derivatives, you have various options to do it. So we stay with the partial derivatives first. We prove lots of things. And in science, that would be fine. But then we should go back and handle the derivatives. So that would take us some time to do it. So the thing that we would like to do before your quiz is partial derivatives. 13.3, it's easy. So I do the partial derivatives, 13.3, and this is where we are going to give you the quiz. Then we can go over some of these problems again on Thursday, okay? So the final target for this week is section 13.3, partial derivatives. We do it tomorrow, and then we give you some time to be able to catch up. Okay, that's it. Any question? So take these sections, just read them carefully, because most of the problems in your next test and the quiz are coming from these two sections, or at least you get 4 or 5 questions. Okay, and especially the method that we talk about is going to be with us through this 3 chapter. So if you haven't done your test, make sure you do it. This is the second day, second option, and tomorrow is your last option to take your test. And I will go back to the campus and collect your papers tomorrow or early or Thursday. Then I will grade it over the weekend. Then you will see your grade. Okay, have a good one, and let me know if you have any question. And see you tomorrow. If you haven't done your test, good luck with your test, or if you've done it, well done. Okay, see you tomorrow. Bye-bye.